And number 4, acid rain can form in a two-step process producing, well, that's nitric acid. It's HNO3. Okay, again, you don't actually have to know anything about acid rain. You don't have to know what the name of that substance is. You just have to do stoichiometric calculations, right? Focus on what you're being asked to do, and don't get caught up in the things that you don't know anything about or we haven't worked on in class. So we start with a car burns 420 grams of N2 according to the above equations. Okay, this is something that's a little bit different. We have one equation and two equations. This is actually going to have something tricky and new to do here, but it's a little bit on the simpler side. It might not be intuitive, but I guarantee this will be easy for you. How many grams of HNO3 will be produced? Right, so we got a gram to gram conversion to start. Okay, gram to gram. So we are going to use multiple conversion factors. Now, there will be one difference, however. We're going to have to use a conversion factor that allows us to go from one equation to the other equation, which is a type of mole ratio. So I'll show you what I talk about when we actually set up the conversion here. So we are given grams of N2. We certainly know that grams of N2 need to be on the denominator of our first conversion factor, and moles of N2 need to be on the numerator. Well, we don't want to be in moles of N2. We want to convert to moles of HNO3. Well, notice there is no setup that allows me to go from this species to HNO3 because HNO3 is not in equation 1. HNO3 is only in equation 2. What I can do, however, is I can use the mole ratio not between N2 and HNO3. That'll get you a slightly incorrect number. I can use the mole ratio to convert from moles of N2 into moles of NO2. Now you might be thinking, Johnson, the question is not asking for NO2. Why would I convert into NO2? Well, hear me out. If I use a mole ratio relating these two substances within the same chemical reaction, can't I use a mole ratio to relate the same species in two different reactions? Right? Because nitrogen is going to go through this change and become NO2. It's this NO2 that enters into the second equation. So these equations are connected, but at a 2 to 3 ratio. Right? So it's a mole ratio not connecting different substances within the same equation, but in different equations relating the same substance. Right? It's kind of straightforward. Don't get me wrong, it's not intuitive, right? You shouldn't have just guessed that off the top of your head. But your textbook is going to indicate this, one of the example problems, and I'm telling you right now. So let's continue to set this up. Now, like I said, I'm going to go from N2 to NO2, and then from that NO2 to that NO2. Okay? Moles of N2 into moles of NO2, and I'll just say from the first equation. And now I'll be in moles of NO2, but in the second equation. Okay, but in the second equation now. Now I can go into moles of HNO3, convert out of moles of HNO3 into grams of HNO3. And I'll be in grams of HNO3. Okay, so we have one extra step. It's this weird thing right here that is going to be a bit different here. So we have molar mass, right? And then we have a couple of different mole ratios. We have two different mole ratios. One mole ratio is letting me go from the given into a middleman, right, the NO2. And then the second mole ratio conversion factor is letting me go from the middleman into the actual unknown that the question is asking me for. So let's plug in the numbers that we have. Now this is 3 significant figures, so I'm just going to plug in molar masses to 3 significant figures, right? Because I know my answer is going to be in 3 significant figures. So 1 mole of N2 has a mass of 28.0 grams. Now we'll start with some mole ratios. That's a 1 to 2. 1 to 2. Again, that's NO2 in the first equation, so that's a 2. Then we have moles of HNO3 to moles of NO2 in the second equation. Okay. Again, here's that 2 to 3 ratio right there. See how we've actually worked in a 2 divided by 3, a 2 to 3 ratio that this connection also requires of the equations. But now, notice all my units canceling. Now I've gotten rid of moles of NO2, and now I'm in terms of the HNO3. And I can easily plug in the molar mass, the mass of 1 mole of HNO3, was it 63.0, I believe? Yes, hopefully. Let's double check that because I messed one up earlier on this worksheet, so let's not do that again. So we get a 14.0 plus 3 oxygens in parentheses plus hydrogen. Yep, 63. Moles of HNO3 will cancel. And now I'm set up to do some calculator work. Again, my answer is going to be in terms of 3 significant figures. 420 multiplied by 2 multiplied by 2 multiplied by 63 divide by 28 divide by 3, and I end up with 1,260. Now, as long as I do not put a decimal at the end of that number, this only has 3 significant figures because that 0 is not significant. So I can be done right here, or if you're a big fan of scientific notation, which some college professors are, 1.26 times 10 to the third grams. All right, part B. For the above reactions to occur, O2 must be in excess in the first step, right? The first equation, O2 is what we were tracking, right? We actually burned this much. Well, in order to burn that much, we're going to have excess. We have to have leftover O2. So we were assuming that there was a whole bunch of this left over and that N2 was limiting. So if we assume that N2 was limiting, that means that the given amount is how much reacted. So we can start from grams of N2, which is what part A gives me. Now I can convert, or I'm going to immediately convert out of grams of N2 into moles of N2. So I can use the mole ratio between N2 and O2. Now I have one more step because this question is asking in grams. Okay, don't forget that the question is asking in grams. So I'll go moles of O2 to grams of O2. See if everything cancels. Grams cancels the grams, moles with moles, moles with moles, and we are in terms of grams of O2. Looks like we're looking good. Again, this first data was given to me 3 significant figures, so my final response will be in terms of 3 significant figures. So let's just pay attention to that. Now let's start to plug in. 420 decimal, that means 3 significant figures. 1 mole of N2 is 28 grams of N2, 3 significant figures. My mole ratio is 1 to 2. And then for every 1 mole of O2, it's 32 grams of O2. Again, oxygen's diatomic molecule. It's the mass of 2 oxygen atoms. So we're ready to use calculator. Multiplied by 2, multiplied by 32, and then divide by 28. We end up with, remember, 3 significant figures. In order to make that last 0 significant, I include a decimal. Last thing, part C. What volume does the amount of O2 in part B, right, what we just did, occupy if its density is 1.4 grams per liter? Okay, remember, Remember that stuff? To be perfectly honest, I'm not exactly sure why I included this. You don't have to remember this. This is true at standard temperature and pressure. Again, you don't actually know what that means, but this gives me information that I need without having to know what the temperature and pressure are. Okay, so we're not actually using this. Okay, you use this statement of equality when the question will say at STP, standard temperature and pressure. This, however, is not at standard temperature and pressure. I believe this is actually a little bit over standard temperature and pressure. Now, whether the temperature is a little bit higher or the pressure is a little bit higher, it doesn't matter. This is actually telling you the gram to liter relationship. So, again, we just generated, we just figured out that we're using 960 decimal, right, grams of O2. Let's convert out of grams of O2 and into liters of O2. How can I do that? Because this little gold nugget right here allows me to relate grams to liters, That'll allow me to have grams cancel, and my answer will be in terms of liters of O2, and that is exactly volume of O2. That's what's being asked. Now, what do I plug in? What's the number in front of grams? 1.4. What's the number in front of that liters? It's a per liter, so it's always per 1 liter. So this actually ends up being a very, very simple calculation as long as you know what to do with this piece of information. Again, follow the units first. Here, I'm given 2 significant figures there, so my answer is going to be reported in 2 significant figures. Just a heads up there. All right, so 960 divided by 1.4. Holy cow, I only need 2 significant figures. So I would need to stop there. That 5 tells me to round that up, so I'm going to go 690. 690 with no decimal point behind that 0, so that 0 is not significant, and that'll allow my answer to stay with 2 significant figures. Or you can always put it in scientific notation. In this case, it would be 6.9 times 10 to the second liters. All right, guys, that's going to do it for section 3. We had some limiting reactant problems. We actually had some problems that asked about excess reactant. We did a little work with percent yield. Please notice factor label method, factor label method, factor label, factor label. Okay, factor label, percent yield. Okay, percent yield. We have a very limited number of functions that we're going to carry out here on this quiz. The key here is identifying what is the limiting reactant, what is the excess reactant, and know that the amount of the limiting reactant is how much is going to react, right, when determining your theoretical yield. All right, guys, not only 4 problems, but a lot of work to be done. So good luck, and I will see you next period.